Hi, in this segment we'll start looking at the function for generating the mesh and for defining the boundary conditions. All right, so let's look at the code. Generate mesh, there's actually not a lot for you to do. I have this global variable L. You remember I declared above, it's a class object, a class variable. So you simply have to define the length of the domain. I'm assuming that the value of x at the left of the domain is 0, and then of course the maximum value of x would be L. From there, I take that x min and x max and I create these DL2 points. A point in DL2 it's essentially a location vector, a position vector. The dimension, or the number of components in the point, is defined by dim in this case, and it holds doubles. I don't use point a lot in this template. You actually won't need to use it at all yourself. But that is the input that DL2 requires to create the mesh. All right, so I take the limits of the domain, which you define here with L. And remember, the input is an unsigned int called number of elements. In main.cc, remember, I had put in 15 as an example, but that just gives the number of elements in our mesh. All right, and then DL2 will use that number to create a mesh. It stores that again in triangulation, which again is a class object. All right, so not a lot for you to do there, but an important step. A lot of it is, again, DL2's functions. All right, now in define boundary conditions, there actually isn't anything that you need to do in this function for this assignment. However, for the future assignments, you will be writing the define boundary conditions function yourself. It will be very similar to this function. But again, you don't have to change anything here, but I want to step through it with you now because, again, you will be using it in future assignments. All right. So here we're using that boundary values map that we talked about, and we already talked a little bit about how the map itself works. However, because of the way DL2 does their node numbering, instead of simply saying, okay, we know how many nodes there are, so I'll just do boundary values at 0 is equal to the fixed boundary condition of 0. And if I have a Dirichlet boundary condition on the right, then I'll just take the last node. But again, since they aren't numbered sequentially, we can't just take the highest node number, because that's not necessarily the last node in the domain, right? So again, as an example, let's create a domain here, and I will, for simplicity, I'll create 4 elements. And on the top, I'll do the x coordinate. So this isn't the real domain. We're going 0, and I'll go from 0 to 1. That would make these 0.25, 0.5, and 0.75. And just to make my point about the node numbering, I'll make this quadratic basis functions. And so we have one mid-side node. Down here, I'll put the node number. Of course, in DL2 node numbering. Okay, so it's 0, 1, 2, 3, 4, 5, 6, 7, 8. Again, so at this node, assuming we're doing 2 Dirichlet conditions, we want to fix this node. And at this, let's say we want to apply a displacement of 0.1. That's a pretty big displacement here, actually. So since it's linear elasticity, I'll do 0.01. So let's say G2 is equal to 0.01. All right. So what we want to do is boundary values of node 0 is equal to 0, and boundary values of the last node, which in this case is actually node 7, not node 8, is equal to 0.01. These are semicolons. And so since we don't necessarily, okay, for the 1D case, we can keep track of the way DL2 is numbering their nodes. However, once we get to 2D and 3D, it gets more complicated from there. So instead what we're doing, and what I'm doing in the code, is I just have a for loop. And I'm looping over all of the nodes. So you can see here I have unsigned int globe node equals 0. So I'm starting at the global node of 0. And I'm looping up through node location.size. Remember, node location.size is a vector of the locations of the nodes. All right, so let me write out what node location, what this vector would look like. In our case, the actual data that it's storing. Okay, so we have node location. And this is what it's holding. Okay, so it's hold for node 0. Again, looking at the indices are these node numbers down here. So for node 0, we're holding a value of 0. For node 1, the x-coordinate is 0.25. For node 2, it would be 0.125. All right, and that goes on until node 7, which has a value of 1, and then node 8, which would have a value of 0.875. Right. Okay, so those are the entries in node location. Okay, and so the length, you can see there it's a length of, it has a size of 9, which is, of course, equal to the number of nodes in the system. Okay, so here in the function define boundary conditions, we're simply looping over all of the nodes using this node location vector. And then we have an if statement. If the value stored in node location at the current node that we're on is equal to 0, in other words, if we're at the left end of our domain, then we set boundary values of whatever the node index is equal to G1. And actually, I could do here an else if I wanted to. Else if, or just if, node location at our current node, wherever we happen to be, is equal to L. In other words, if we are at the right side of our domain, and if problem equals 1, in other words, so problem 1 is where we have two Dirichlet boundary conditions. So if we have a Dirichlet boundary condition in our problem, and we are at the right-hand side of our domain, then we will store the Dirichlet value of G2 in our domain. So that's this one here. Okay, so again, there's nothing you have to edit here, but it's good for you to understand what's happening so that you can use it on the next homework assignments. All right, let's move on, and in this segment, let's still look at setup system. Okay, so in setup system, first we have to define, again, we were using G1 and G2 in the previous function. Here's where we actually define what those values are. And you'll have to look in your homework assignment to see what those values will be. Of course, in problem 1, we use both G1 and G2. In problem 2, G2 won't actually be used because it's a Dirichlet-Neumann problem. But you can still use the same value of G2, right? Okay. This next line is just DL2 distributing the degrees of freedom. It's just keeping track of degrees of freedom. Now here, there are several lines going on here, but essentially all I'm doing is I'm creating this vector node locations, which holds the x-coordinates for each global node, again by its global index. Now that those structures are defined, now we will call this function define boundary conditions. Okay, notice that since we are still within another class function itself, we don't have to create like problem object. We don't have a class name since we're not dealing with an actual class object yet. So we don't have this problem object dot define boundary conditions. We can simply use the function name itself because it is also an FEM class function. Okay. All right. So we call that function, which is the one we were just talking about. From there on, this next section just has to do with resizing the matrices and vectors. You can see rather than using the function .resize, which is what standard vectors use, the DL2 vectors and matrices use .reinit, short for reinitialization or reinitialize. And we use this DOF handlers .ndofs. That gives us the total number of degrees of freedom in our domain. Since we have 1 degree of freedom per node, it's the same as the total number of nodes in this problem. All right, now here we define the quadrature rule. And I set up a quadrature rule of two quadrature points per element. However, that's not going to be enough. Remember that for the quadrature rule, let's say you have a quad rule. Oops. A quad rule. Let's say you have a quad rule of 2. This is actually good for an integrand of up to third order. So remember that good for an integrand of third order, or third order polynomial. All right. So remember that this Gaussian quadrature is exact for polynomials of order equal to 2 times the quadrature rule minus 1. So in this case, if you have a quadrature rule of 2, it's good for an integrand for a third order, right? Because 2 times 2 is 4 minus 1. So if you have an integrand of order 3 with polynomials of order 3, then Gaussian quadrature will integrate exactly for you. Okay, but remember you'll be using not only linear but also quadratic and cubic basis functions, and you'll be doing an L2 norm. Okay, so you have to, in each of these cases, don't look actually just at the order of your basis function. Look at the whole order of the integrand that you're integrating, okay? And once you know that order, that polynomial order, then you can decide what quadrature rule order you need. Now, having said that, you don't have to necessarily change your quad rule for each problem. You can decide what's the maximum quadrature rule that you need, and that actually will come from the L2 norm using cubic basis functions. You can decide what quadrature rule that is. Is it 4? Is it 5? Is it 6? Decide what that number is, and then you can use that quadrature rule for all of your problems on homework 1. Okay, for whatever basis function order. All right. So again, you'll define that here. So you would change quad rule to whatever value you want. And then quad points and quad weights are again just vectors. You put in so quad point stores the values of xi for each quadrature point. For 2 point, it's minus square root of 1/3 and positive square root of 1/3, and the corresponding weights are 1. Okay, if you go to a higher quadrature rule, then you will obviously create a longer vector. You can see that here I do quad points.resize, and I resize it according to the quadrature rule that you define up here. Okay, so it will automatically go to the correct length. You have to define the correct values. And those can be found online or in a book on finite elements or on numerical integration. All right? Okay, so let's stop this segment here. And in the next segment, we'll move on to the assemble system function, the assembly function, which involves creating F local and K local.